Okay, we are doing section 2.08 limits. And so, a lot of limits, just to make sure that we get it right, we can evaluate the limits in our calculator. And this actually gives us a pretty intuitive understanding of what a limit is. So, for the first function, we have fx equals 70 over the quantity of 1 plus 9 times the quantity of 0.55 to the x power. So to evaluate this function, we can plug it into our calculator. We will have 70 in our numerator, and then 1 plus 9 times the quantity of 0.55 to the x power in the denominator. Now we're going to go to the table set. To evaluate the limit as x approaches negative infinity, we'll just pick a very large value for x. So let's do negative 2,000. The delta x be 0.1, and then evaluate it at the table. Now, at this value, it becomes an error because it becomes so small already. So if we change the table set to something more modest, like negative 100, still an error. So change this table set again, go from negative 1,000 to negative 100. You can say this becomes a ridiculously small number. So let's say x is equal to negative 100. This means when x equals negative 100, y is equal to 8 times 10 to the negative 26. So that would be, that's equivalent to 0.0000000, 26 zeros, 25 zeros, but 26 zeros and then an 8. So that's pretty much 0. And if x becomes negative infinity, it's definitely going to be equal to 0. So the limit as x approaches negative infinity is equal to 0. And that's the limit as x approaches negativity of f of x is equal to 0 as x approaches negative infinity. Now we're going to look at when x approaches infinity. So we're going to look at the limit as x approaches infinity of f of x. So now let's try when, table set, instead of x being negative 100, x is, let's try 200. Second table. 70. So as soon as x gets large enough, y is equal to 70. So, limits of x as x approaches infinity, limit as x approaches negative infinity of f of x is equal to 70. So the limit as x approaches negative infinity of f of x is equal to 0, and limit as x approaches infinity of f of x is equal to 70. That's going to be answer choice B. Alright. Let's go to problem 2. The piecewise function below, k is constant. So what is the value of the limit as x approaches k from the left? Alright. Well, what we can do is we can pick a number for k. So let's pick a number for k, which is going to be 1. So let's say k equals 1, and then what we can do is we can evaluate this top value, because really when we're looking at this function, f of x is going to be equal to 4 minus k only when x is equal to k. So when, for example, when x is equal to 1, y is equal to 4 minus 1, which equals 3. So yes, you have when x equals 1, y is going to be equal to 3. But for the entire rest of the function from negative infinity to 1, and then 1 to infinity, f of x is going to be x squared minus k squared times x minus k. So this is what we're really looking at when we're coming from the left. So let's evaluate x squared minus k squared over x minus k when k equals 1. So we're going to evaluate x squared minus k squared over x minus k when k equals 1. So what we can do is, into our calculator, plug that function in. X squared minus 1 squared over x minus 1. Alright, so now that we have the function in our calculator, we can go to second table set, and we're approaching the function as x approaches 1 from the left. So we're going to be, the table start is going to be at 1, and the delta table is going to be, let's do 0.01. And then we evaluate the table on our calculator. Okay? So even though as x approaches at 1, there's an error, right to the left of 1, at 0.99, the function is equal to 1.99. So, to the left of 1, when x equals 0.99, y is equal to 1.99. And what that means is that really we need to find the relationship of our k value to our y value. And essentially what this calculator is, and what we're getting at, is that as x approaches k from the left, well k is equal to 1, y is going to be equal to 2 times 1, or it's equal to 2k. So the answer choice is going to be B. Okay, so that's number 2. What is the value of the limit as x approaches negative 2 of 3x squared minus 4x plus 6? Well, we have 3x squared minus 4x plus 6. So that's going to be, we plug that into the calculator, 3x squared minus 4x plus 6. And so then, what we can do after that is we're approaching negative 2. So we go to second table set, table start, negative 2. And we evaluate the table. When x is negative 2, y is equal to 26. So all the instructions here is that input function into calculator, table set, and then you can have your table start at negative 2, your delta table be 0.1, and then evaluate in table. The answer is going to be 26. So there you go. What is the value of the limit as x approaches 5 of x squared minus 7x plus 10 over x minus 5? So, let's evaluate. In the calculator, we can do x squared minus 7x plus 10 over x minus 5. Now, we go to second table, and we're going to table set, and our table start is going to be at 5. So now when you evaluate the function, at 5 there's an error. So let's read out the table. So we can say, we enter into the calculator, so we say evaluate in calculator, and then we have our table. And in our table, we have x at 4.99, 5, and 5.01, and our y value is going to be 2.99 error and 3.01. So notice, even if when x equals 5, error means that the function does not exist, as x approaches 5, just 1 unit, 0.01 units to the left and right, we have y is equal to 2.99 and 3.01. So because of that, we know that the function is going to be approaching 3. Because just to the left and to the right of 5, the function is still approaching 3. So the answer is going to be 3. Okay, we'll go on to the next page now. A piecewise function is shown below. F of x is equal to c of x plus 1 where x is less than or equal to 2, and c of x minus 1 when x is greater than 2. For what value of c does the limit of x approaches 2 exist? So in order for this limit to exist, we need to meet some conditions, and that means that the function has to be continuous at 2. The function needs to be, in order for the limit to exist when x approaches 2, that means that f of x needs to be continuous at x equals 2. So we need to find a value of c that makes f of x continuous. At x equals 2. So we evaluate each function at 2, and we need to find a value of c that works. So let's do first c for c of x plus 1 when x is greater than or equal to 2. When we evaluate that, it would be c of 2 plus 1, which is going to be equal to 2c plus 1. And when we have cx squared minus 1, that's going to be c times 2 squared minus 1, which is going to be equal to 4c minus 1. So we need these, in order for these values to be continuous, these values must be equal to each other. So we have the equation 4c minus 1 equals 2c plus 1. So what we can do is subtract 2c from each side. So we can have 2c on this side, and we can add 1 to each side. So that cancels out. This cancels out, and you have 2c is equal to 1 plus 1 is equal to 2. Divide each side by 2. And we can have c is equal to 2 over 2, which is equal to 1. And that's our answer. C, 1. Now, we can say, what is the value of limit as n approaches infinity of 3n minus 1 over 3n? Okay, well, just analytically, as n approaches infinity, that minus 1 in the numerator is going to become irrelevant. So therefore, the limit as n approaches infinity is going to ultimately approach something like 3n over 3n, which is going to be equal to 1. So that's going to be C. You can also evaluate the function in the calculator, so you can do three to the x minus 1 over 3 to the x, and go to table set, evaluate the function in a very large number, like let's do 5,000, and then when we evaluate the function, or that becomes so big. But if we do something a little bit more manageable, like let's just do 500, still too big for the calculator to keep track of. Let's do something like 50. 1, okay? So the function it's too big for the calculator to, the values of the numerator and denominator get too big when x is equal to too big of a number. But even at something like 50, we see that it approaches 1 when n gets big. Okay. Let's go to problem number 7. Let w sub 0 equal 100 and wn equal 0.95 wn minus 1 plus 80. What is the value of wn as n approaches infinity? This is a very tricky problem. So, one thing that we have to know is that as n approaches infinity, an, or I should say wn, is going to be equal to wn minus 1. So as n gets infinitely big, if n is really infinitely big, then the infinite term is equal to 1 less than the term before it. So we can say that wn is equal to wn minus 1. In the equation we can set up with that, wn is equal to wn minus 1, we can say that 0.95 w to the n minus 1 plus 80, so that's wn, right? We can say that's equal to wn minus 1.